Right. So in the last class, we saw this theorem, which I just stated, that allows us to define a class of random variables for which the tail probability decays at least as fast as that of a Gaussian. All right, and we call these Subgaussian random variables. So effectively, a Subgaussian random variable is one. You can treat this as the definition of a Subgaussian random variable. Any random variable for which this particular quantity, expectation of e raised to x square by some constant, is less than or equal to 2 for some finite constant k4, you can call this a Subgaussian random variable. Right? And a Subgaussian random variable satisfies all of these properties. Now I could define a Subgaussian random variable using any of these 5 properties or 4 properties mainly. But for whatever reason, I'm going to take this as the definition, and using this I defined what is called a Subgaussian norm. Right? It's the smallest value of k, the smallest positive k, for which expectation of x square by k square is less than or equal to 2. Alright? And we made some very basic observations about Subgaussian random variables and the Subgaussian norm. We saw that if x is a Subgaussian random variable, then alpha times x for any real number x, for any real number alpha, this is also a Subgaussian random variable. And the Subgaussian norm of alpha times x is just mod alpha times the Subgaussian norm of x. Okay? And as we saw, a Gaussian random variable is Subgaussian. And in fact, we computed the Subgaussian norm of a normal random variable. So the Subgaussian norm of a random variable which is Gaussian with 0 mean and variance sigma square, this is equal to 8 sigma square divided by 3. Okay. And towards the end of the last class, I've been calling this quantity a norm. Right? The smallest k positive for which expectation of x square by k square is less than or equal to 2. I called it a norm. But then for something to be called a norm, it has to satisfy certain properties. So firstly, it should be non-negative and should be equal to 0 if and only if it's equal to the 0 vector. So typically a norm is defined over some kind of a vector space. And for any real number alpha, f of alpha times x, the norm of alpha times x should be mod alpha times the norm of x. And the norm should satisfy a triangle inequality. Right? It's only if the function over this space satisfies these 3 properties can I call it a norm. And so let's prove that the Subgaussian norm is in fact a norm. We've already seen one property, that is f of alpha times x is equal to mod alpha times x. Alright? Yeah.
In that Subgaussian norm, so we have defined it as argument of greater than 0. And we are saying we cannot have a 0 condition. And wouldn't that make Subgaussian not a norm?
So let me be a little more precise. Okay. So the Subgaussian norm is defined as the infimum over all k greater than 0 for which expectation of e to the x square by k square is less than or equal to 2. Okay, so this is the formal definition, and this infimum versus minimum is really what makes the difference. In particular, so suppose that, so if you take a look at this particular quantity, right, this is a set, correct? And in particular, what kind of a set is it? So if some particular value alpha belongs to this particular set, then does any value greater than alpha also belong to this set?
Defining.
Yeah? No?
No, not defining. Alpha is the minimum value, then we are meeting.
No. I'm just talking about this particular set over here, right?
Yes. Great.
Correct. Let's call this set, I don't know, let's give it a name. Let's say A subscript X. Okay, so A subscript X has the property that if you take any value alpha in A subscript X, then everything to the right also belongs to A subscript X. And it's a subset of the positive real line. So what can you say? What does the set look like? Irrespective of what the distribution is. Right? If X is a Subgaussian random variable, what kind of a set is A subscript X?
Set of real numbers greater than a particular number.
Correct. So it could take one of two forms. It could be of the form alpha comma infinity, right? Or it could be a completely open set. Right? So in both of these cases, what would the Subgaussian norm be equal to? Suppose that this set A subscript X has the form, let us say, alpha comma infinity, then what is the Subgaussian norm equal to? It will be the value alpha, right? Irrespective of whether it is this set or this set. Correct? So in particular, even though this particular set cannot be equal to 0, it could potentially be of the form 0 comma infinity, open from the left. Okay? In which case the Subgaussian norm can be equal to 0. Okay, that's the only situation where it can be equal to 0. Right? You are right about the point that the set cannot contain 0. All right? Did that answer your question? Okay. So in fact, it's clear that the Subgaussian norm is greater than or equal to 0 for any random variable x. That much is clear. Okay. So when can it be equal to 0? Let's suppose that x, when do you think the Subgaussian norm should be equal to 0? Can you guess? Yeah? 0? It should be 0 with probability 1. Right? Suppose x is equal to 0 with probability 1. Right? Then what can you say about expectation of e to the x square by k square for any k positive? It's equal to 1. Right? Greater than 0. So this set A subscript x essentially is the entire positive real line. Okay. In this case, so what is the Subgaussian norm of x? It's equal to 0. Right? But is this the only situation where the Subgaussian norm can be equal to 0? Because after all, for it to be a norm, what we have to show is that the norm takes value 0 only if x is equal to 0. I've shown that if x is equal to 0, then the norm is equal to 0. Right? So let's suppose that the probability that x is not equal to 0 is positive. Okay. Now, it doesn't mean that x is a non-trivial random variable. In principle, x could also be equal to some positive constant or some negative constant with probability 1. All right? Even that is considered by this particular condition. Okay, so this means that there should be some epsilon, right, positive, and some delta positive, no matter how small these values are, such that the probability that x square is greater than epsilon square is at least delta. Right? I'm looking at a very small neighborhood of 0, right? And if the probability that x not equal to 0 is positive, then it means that there should be some probability, some non-trivial probability, delta probability in the region outside minus epsilon to plus epsilon. Right? So basically, if I take the real line, this is 0. Alright, so this is minus epsilon and plus epsilon. Then the total probability over this entire yellow region should be at least delta. I can find some epsilon positive and some delta positive. Epsilon could be 10 to the minus 7 and delta could be 10 to the minus 9. Doesn't matter. It's something that is positive. Okay. So then the expectation of x square divided by k square, this is at least one times the probability that x is equal to 0 or plus the probability that, or let me simplify it even further. So let's see, what is the expectation of x square by k square? If it's a continuous random variable, then this is integral from minus infinity to plus infinity e power x square by k square fx of x dx, right? Which is greater than or equal to integral from, let's say, x such that x square is greater than or equal to epsilon square e power x square by k square fx of x dx. The integrand is non-negative, so if I integrate over a smaller region, then the integral can't be any smaller, it can only be larger. Alright? Okay, so this is, now in this region, this is at least e to the power of epsilon square by k square. Right? Correct? And this is nothing but e to the power of epsilon square by k square times the probability that x square is greater than or equal to epsilon square. Right? But this is e to the power of epsilon square by k square. I assume that this quantity, probability that x square is greater than or equal to epsilon square, is at least delta, or some delta positive. Now if I look at the right hand side, what happens as I let k to tend to 0? Yeah, So eventually at some point it should be larger than 2, because the right hand side, it's a monotonically increasing function of k, right? So as k tends to infinity, the right hand side tends to infinity. At some point it should hit 2, right? So I can't have k to be arbitrarily close to 0 and yet have the right hand side less than 2. Alright, so this quantity is strictly greater than 2 for small enough k. Which means that the Subgaussian norm is not equal to 0 for this particular random variable. Okay, so we've basically shown that the Subgaussian norm satisfies this property as well as this property. All that's left is to show that it also satisfies a triangle inequality. Right? And these properties will be particularly useful when we want to derive tail bounds for various classes of random variables. Okay, so the third property is, suppose that x and y are Subgaussian random variables. Okay, remember that x and y need not be independent of each other. They could have any arbitrary joint distribution. And let's use some notation. Suppose that the Subgaussian norm of x is kx and the Subgaussian norm of y is ky. Both of them are finite and positive. So the key trick to using or to proving that this is actually that x plus y is also Subgaussian and that the Subgaussian norm of x plus y is upper bounded by the Subgaussian norm of x plus the Subgaussian norm of y is the following. So the function, let's define the function f of x, or let me call it g of x, to be e to the power of x square. Alright, so this function, I claim, is increasing, which is clear, and it is convex. Okay, you can just find the second derivative of g and then show that it is positive. Alright, and so this is an increasing and convex function, and therefore it also satisfies, you can use Jensen's inequality, but at the same time I don't even need as much as the full power of Jensen's inequality. I just need the fact that g of alpha x plus 1 minus alpha y, this is less than or equal to alpha g of x plus 1 minus alpha g of y for any alpha that is between 0 and 1. Okay, so these are all the tools that I need in order to prove triangle inequality. Okay, so now So let me take in g of x, let me take g of mod x x plus y divided by kx plus ky. So if I'm supposed to show that, or if I want to derive that a triangle inequality, what do I want to show about g? Or what do I want to show about this particular quantity? Yeah? Let's not worry about how I'm going to simplify this, but what do I want to show ultimately? Not really. So this is what? This is e to the power of x plus y the whole square divided by kx plus ky the whole square. So if my hypothesis that the triangle inequality indeed is satisfied, then what should then what should the right hand side be equal to or less than or equal to? Or what can I say? 1? What do I want to show? I want to show that the Subgaussian norm of x plus y is less than or equal to kx plus ky. Alright? So what does triangle inequality say? Or which is equivalent to showing that expectation of e to the power of x plus y the whole square by kx plus ky the whole square is less than or equal to 2. Okay. So by definition, the Subgaussian norm of x plus y is the smallest value of k for which this quantity, that this expectation is less than or equal to 2. Right? So if this holds for kx plus ky, then obviously the Subgaussian norm can only be less than kx plus ky. Is that okay? So my goal is to show that expected value of g of x plus y by kx plus ky is less than or equal to 2. So this, no, I need to show a bunch of steps. So I know that g is monotone, alright, and I know that mod of x plus y is less than or equal to mod x plus mod y. Right? So this is less than or equal to g of mod x plus mod y divided by kx plus ky. Okay. This is nothing but g of mod x. I'll split this into 2. Mod x times 1 by kx. Let me write it. This is g of mod x by kx plus ky plus mod y by kx plus ky. I'll multiply and divide by kx for the first term and multiply and divide by ky for the second term. kx by kx plus ky times mod x divided by kx plus ky by kx plus ky times mod y by ky. I've done nothing here except manipulate the terms. Now by convexity, right, this is less than or equal to. Now if I take this particular term to be equal to alpha, and so this term is nothing but 1 minus alpha. This is less than or equal to kx by kx plus ky times g of mod x by kx plus ky by kx plus ky g of mod y by ky. Right? And I just take expectation on both sides. I have expectation of e to the power x plus y the whole square by kx plus ky the whole square is less than or equal to kx by kx plus ky times expectation of g, which is nothing but e raised to x square divided by kx square plus ky by kx plus ky expectation of e raised to y square by ky square. What do I know about this term? It's less than or equal to 2. What do I know about this term? This is also less than or equal to 2. So I get this is less than or equal to 2 times kx by kx plus ky plus ky by kx plus ky, which is less than or equal to 2. So therefore, the Subgaussian norm of x plus y is less than or equal to kx plus ky. Okay, so this particular statement is pretty powerful. It says that irrespective of the joint distribution of x and y, as long as their marginals are Subgaussian, the sum is also guaranteed to be Subgaussian. And you also have a bound on what is the Subgaussian norm of this particular random variable. So if you combine all of these, then if x1, x2 up to xn are Subgaussian, with, let's say, ki to be the Subgaussian norm of xi, and alpha 1, alpha 2 up to alpha n are real numbers, x1 through xn need not be independent of each other. Then this linear combination alpha I summation over I alpha I xi is also Subgaussian with the Subgaussian norm to be less than or equal to summation mod alpha I times the Subgaussian norm of xi. This is K. Now this is particularly powerful because I can now use these equivalence properties of Subgaussian random variables. I know that if I have a bound on the Subgaussian norm, then I automatically have a tail bound on this particular random variable. So if I have a tail, so if I know that x1 through xn are Subgaussian, then I also have a tail bound on any linear combination of these random variables, even if they are not independent of each other. So right now we've gone beyond what we've seen so far, beyond what the standard Chernoff bounds can do. Chernoff bounds can only give me exponential tail bounds for sums of independent random variables. But now even if they're dependent, I do have a tail bound. Right. Maybe I'm not able to characterize the exact constants in that particular tail bound, but that's not a big issue. Right. But I know this up to a universal constant. Remember that the constant here is different from the constant here, but you can take them, the ratio of those two constants is something universal. It does not depend on the distribution of xi. Questions?
Also, previously we could scroll up.
Sure. The theorem?
Yes, the proof for E of for the Subgaussian triangle inequality proofs.
Yes.
So we can only use that to prove that that's less than or equal to 2. How did we? That means kx plus ky is a solution which satisfies less than or equal to 2. How did we prove that the Subgaussian norm x plus y is less than or equal to kx plus ky? Because that last statement only gives kx plus ky is a solution for less than or equal to 2.
No, right? So basically this is some value of k. Expectation of x plus y the whole square divided by k square is less than or equal to 2.
That will only get a solution that kx
Correct.
plus ky is
Right? So which means that this particular k equal to kx plus ky belongs to this set ax. Alright? And everything to the right also everything to the right of kx plus ky also belongs to ax. But the Subgaussian norm is the smallest such value of k. So the smallest such value of k can only be less than or equal to kx plus ky. So the Subgaussian norm has to be less than or equal to kx plus ky. That's it.
And is the equality hold?
Which one?
The Subgaussian norm of x plus y plus.
Okay. So here is one perhaps example. Let's take x and y to be so in fact to answer that let's look at what is the Subgaussian norm of a constant random variable. Okay. So let's take x to be equal to some alpha with probability 1. Right? Now, what is expectation of e raised to x square by k square? This is just e to the power of alpha square by k square. Alright. So, what can you say about the Subgaussian norm of x. This quantity should be less than or equal to 2. In fact, it's that value such that this is equal to 2. Equal to 2, which means that alpha square by k square should be equal to log 2, or the Subgaussian norm is just mod alpha divided by log 2. Correct. Square root of log 2. Right? Now, suppose that x and y are both constant random variables. Okay, let's take, let's say positive. Take x equal to alpha with probability 1, y equal to beta with probability 1. What can you say about the Subgaussian norm of x plus y?
Less than or equal to Subgaussian norm.
I know, but in this specific case, what will it be equal to? What is x plus y?
Mod of alpha by root ln2.
So let's assume that alpha and beta are both positive.
Alpha plus beta by root
Correct. So x plus y is also a deterministic random variable with so it's equal to alpha plus beta with probability 1. So the Subgaussian norm is alpha plus beta divided by square root of log 2, right? Which is equal to the Subgaussian norm of x plus the Subgaussian norm of y. Right? Now, more generally, let's suppose that x is some arbitrary Subgaussian random variable and y, let's say, is equal to x with probability 1. Yeah, the correlation coefficient is equal to 1 in this case. So what can you say about the Subgaussian norm of x plus y? What can you say about the distribution of x plus y?
So same as 2x.
Correct. So x plus y is equal to 2 times x with probability 1. Right? So what is the Subgaussian norm of x plus y? It's a Subgaussian norm of 2x, which we know is 2 times the Subgaussian norm of x, which is equal to the Subgaussian norm of x plus the Subgaussian norm of y. Okay. So more generally, you'll have the Subgaussian norm, the equality holding when x and y are very tightly correlated with each other. Right? But what happens if x and y are independent of each other?
But then also equality should hold with summation of two separate.
Not necessarily. So let's think about it in terms of what we're already familiar with, which is Euclidean geometry. Alright? If you take any of two vectors in Euclidean space, the kind of intuition you should have is that two random variables are statistically independent should kind of correspond to two vectors being orthogonal to each other. Alright? And what happens, and again in Euclidean space, let's say if you take the L2 norm, then when is the L2 norm, when is the triangle inequality satisfied with equality? Yeah? When they're in the same direction, when one vector is some constant times the other vector, right? Which is something that we've seen here as well. When y is equal to not just x, it could be some alpha times x, right? You have the triangle inequality being satisfied with equality. Now similarly, what happens when x and y are independent of each other? What happens in the Euclidean case? When two vectors are perpendicular to each other, what relationship do you have in terms of the norms of x, y and x plus y? You have a Pythagoras theorem which says that the norm squared of x plus y is equal to the norm squared of x plus the norm squared of y. Let's see what happens in this particular case. Right? So if x and y are independent of each other, then, and we'll also make another assumption over here, something additional is required. X and y, the expected value of x equal to 0, the expected value of y is equal to 0. Okay, that's an additional qualifier that I'll add. What is expectation of x square, so x plus y the whole square? So I want to say something about this particular quantity. Right? This is equal to expectation of e to the x square plus y square plus 2xy divided by k square, right, which is nothing but expectation of e to the x square by k square, e to the y square by k square, e to the 2xy by k square. Right, so this is let me just check this. Okay, so I'd like to take this back a little bit. So now I can't directly take the expectation inside because I have x times y. Alright, so let me take it back. I'll prove something a little bit weaker at the moment. Alright, so let's look at expectation of e to the x plus y. If we go back to the various equivalence properties that we had, right? what we wanted to show is that if x is Subgaussian, then expectation of e to the t times x should be less than or equal to e to the some constant square times t square. Alright? Which means that if x and y are independent and Subgaussian, then expectation of e to the t times x is less than or equal to e to the t square times some universal constant times the Subgaussian norm squared of x, and expectation of e to the t times y is less than or equal to e to the constant times t square times the Subgaussian norm squared of y. So what can you say about expectation of e to the t times x plus y? This is expectation of e to the t times x times expectation of e to the t times y, because x and y are independent of each other. Right? So, and this is less than or equal to e to the constant times t square times the Subgaussian norm of x square plus the Subgaussian norm of y square. Right? So what this effectively allows us to show is that the Subgaussian norm of x plus y squared is less than or equal to the Subgaussian norm of x square plus the Subgaussian norm of y square. Not a full Pythagoras theorem.
Sir, where did you get the first inequality?
Which one? These? These are just by the equivalence conditions, right? So I had this theorem which said that all of these are equivalent, right?
Okay, the last one.
Correct, the last one over here. Right? And basically K5 and K4 are of the ratio between K5 and K4 is some universal constant. That is why I had that C, which is some universal constant here. Okay? So put together, this allows us to prove a rather nice result. Called Hoeffding's inequality. This basically says that if x1 through xn are independent, and the Subgaussian norm of xi is ki, alpha 1 through alpha n are arbitrary real numbers, we'll and let's assume in addition, we'll assume that the expected value of xi is equal to 0. So we've centered the random variable so that the mean is equal to 0. Then the probability that alpha I xi is greater than or equal to some delta is less than or equal to e to the minus some constant times delta square divided by some I equal to 1 to n ki square. Right? And here I've basically used the first property of the theorem. Right? So if x is Subgaussian with parameter k, then the probability that mod x is greater than or equal to delta is less than or equal to 2 times e to the minus some constant times delta square divided by the Subgaussian norm square. Okay, so I should have perhaps have a 2 in this inequality here. All right. Okay. So in fact, I don't even need the assumption that expectation of xi is equal to 0. It very well holds true even if the expectation of x is not 0. But I mean, so far nothing surprising. We've developed a bunch of tools, but in the end, all of this works only if x is Subgaussian, right? Which may or may not be as general as we want. Hoeffding's is known for, I'll get to that in just a minute. Okay, so we know this if for Subgaussian random variables for which we know the Subgaussian parameters. Right? That is the Subgaussian norm. We need to know that x is Subgaussian. We need to at least have a bound on the Subgaussian norm of x. In fact, I can replace this with any upper bound on the Subgaussian norm of xi. The inequality will still continue to hold. Alright, so in fact, in this inequality here, all I need is that the Subgaussian norm is less than or equal to k. Okay, so let's take a very important special case. What if x is a bounded random variable? So x lies within some, let's say, minus alpha to plus alpha with probability 1. Okay, for some positive alpha. Okay, so the probability that mod x is greater than alpha is 0. I don't care what the distribution of x is within this minus alpha to alpha. It could be very weird. That's fine. The expectation of x need not be equal to 0. No further assumptions made. Okay. I want to show that I claim that x is Subgaussian. Okay. And this is where we'll again use these properties. Going back to the theorem out here, we'll use those properties which are easiest to work with, and in particular I'll use property number 2, that expectation of x to the p mod x to the power p whole raised to 1 by p should be less than or equal to k2 times square root of p. So if I have this, I need to get a bound on expectation of mod x to the power p. Now I know that mod x is less than or equal to p, alpha with probability 1. So the expectation of mod x to the power p should be less than or equal to alpha to the power p. Right? For all p greater than or equal to 1, which is also less than or equal to alpha power p times square root of p, because p is something that is greater than or equal to 1. Right? X power p whole raised to 1 by p. Sorry, I think I need p raised to p divided by 2. Because I can multiply with anything that is larger than 1. So this is less than or equal to alpha times square root of p, which again by the theorem implies that the Subgaussian norm of x is less than or equal to some universal constant times alpha. No. When I say it's universal, it is something which does not depend on the distribution. Right? Something like, I don't know, log 2 or whatever.
So the previous C we used and this C would it be same?
Not necessarily. You mean the C over here?
Before that x plus y also we did use one C.
They're all different universal constants depending on which pair of statements you're working with. But for a given pair of statements, it's a universal constant. So I'm not going to particularly keep track of what the value is, but it's something small. Okay. In Hoeffding's. That's correct. So Hoeffding's inequality should have an alpha k square here as well. Okay. So which means that if I want to use Hoeffding's inequality for bounded random variables, I don't even need to know the distribution of the bounded random variable. All I need to know is that the random variable is supported within some particular region. As long as I know that, I automatically have a tail bound. Right? So let's see a quick application of this. And this is a problem of hypothesis testing. So the problem is as follows. You can think of, let's say, trying to find, so earlier we were trying to estimate, say, the bias of a coin. In this case, suppose that there are two coins. One is maybe a fair coin, so the bias is equal to half. The other is an unfair coin. The bias is not equal to half. It's something strictly that's different from half. And your goal is, suppose I toss the coin, say n times. I want you to decide whether it's the biased coin or the fair coin. Okay, so there are two cases. Let's say x 0, 1, maybe this 0 corresponds to the fair coin and 1 corresponds to the biased coin. Okay, but so these two are called the hypothesis. So if x is equal to 0, then y1 through yn are IID distributed according to say p0. And if x equal to 1, then y1 through yn are IID samples distributed according to p1. Okay, so in this case, in the case of say fair coin versus biased coin, y1 through yn are IID Bernoulli half, whereas in this case these are IID Bernoulli p for some p which is different from half. The fundamental assumption that we will make over here is that we know the distributions p0 and p1. Okay, and again for this very specific example that we are considering here, we'll assume that p0 of y is greater than or equal to some p minimum which is strictly positive, and p1 of y is also greater than or equal to this p minimum which is strictly positive. Okay, so for now let's just assume that these are discrete distributions with some finite support. Okay, and so we know p0 and p1, therefore we also know this p min. So the goal is, given y1 through yn, decide if x is equal to 0 or 1. Right? And how do we decide whether a given test is good or not? We just measure what is the probability of error. So we'll assume that maybe x is equal to 0 with probability 1 and x equal to 1 with probability 1. So x is a Bernoulli half, right? So with equal probability you pick the biased coin or the fair coin. The goal is to understand what is the probability that, let's say, you take the samples y1 through yn and output an x hat which is either 0 or 1, that's your hypothesis. What is the probability that this is not equal to the actual x? So suppose that you were faced with this specific problem where you are given a biased coin versus a fair coin, and you have to decide, given a certain number of samples, what would you do?
The average of all the samples and see which is it closer to half or the biased problem.
Okay, so one way is you take the coin, you get n coin tosses, you find the fraction of heads, and you find out whether the fraction of heads is closer to half or closer to p. Right? That's a natural choice. What we'll do something similar but more general. That is, we'll decide, so x hat, we'll take this to be equal to 1 if the probability of observing yn under the hypothesis 1, basically under distribution P1, is greater than or equal to the probability that we observe the sequence yn under distribution 0. Alright, and it's equal to 0 otherwise. Have you seen this before? It's a likelihood ratio test, but many of you have taken digital communications or statistical inference. Okay, so this is effectively a maximum likelihood decoder. Right? But in the case where you only have to distinguish between two different situations, this is what is called the likelihood ratio test. Because I can write this as the ratio of Pyn given 1 divided by the probability of Yn given 0 to be greater than or equal to 1. Alright? Or I'll write it in a slightly more convenient fashion. If log of the probability Yn given 1 divided by probability Yn given 0, this is greater than or equal to 0. Right? But what is probability of Yn given 1 equal to? Assuming that it is actually hypothesis 1, what is the distribution of y1 through yn? Alright, so it is, they're all IID with PMF P1. Alright, so this is nothing but the product I equal to 1 to n P1 of yi. Similarly, if the true hypothesis was 0, then the distribution is product I equal to 1 to n P0 of yi. Now, you have to keep something in mind, that this particular function, right, this is the actual distribution of yi depends on the true hypothesis. So y1 through yn are random variables. So this particular log likelihood ratio, log of the ratio of these probabilities, it's a random variable depending on the realization of y1 through yn. Alright. So my goal is to understand or to find a bound on the probability that x hat is not equal to x. Alright, so this, if I look at log I equal to 1 to n yi by p0 of yi, this is nothing but summation I equal to 1 to n log p1 of yi divided by p0 of yi. This is nice because this effectively is a sum of random variables. And under the assumption that we are in, let's say, hypothesis 0 or hypothesis 1, So conditioned on the actual hypothesis, this is a sum of IID random variables. It's not Bernoulli, some distribution, but then if I assume that the probabilities are lower bounded by something, P1 or log P1 of y by P0 of y, this is less than or equal to, what is the maximum value the probability can take? 1, right? What is the minimum value the probability can take? I've made some assumptions on the distribution, right? I've assumed that the minimum probability is P min, which is strictly positive. So this is less than or equal to log 1 by P min. This is at least log P min. Right? So under a given hypothesis, this particular quantity is a sum of bounded random variables. IID bounded random variables. Now the distribution of this could be arbitrary. I don't really know because I have very general assumptions. But no matter what happens, I know that this is bounded between log P min and log 1 by P min. Right? Which is particularly nice. So the probability of error x hat not equal to x for this particular likelihood ratio test is the probability that x hat not equal to x given x equal to 0 plus probability that x hat is not equal to x given x equal to 1 times x. So we're assuming that x is equal to 0 or 1 with probability half, so it's equal to this. Okay, so let's just look at one particular assumption. So let's assume that let's just analyze one of these terms. The other term can be analyzed in a very similar fashion. So let's assume that x is actually equal to 1 and we want to find what is the probability that x hat is not equal to x. Not equal to x given x equal to 1. When does this happen? When do you, so this is the probability that x hat equal to 0 given x equal to 1. When do you decide in favor of 0? When the log likelihood ratio is less than 0. So log of product P1 of yi given P0 of yi, this is less than 0 given that x is equal to 1. So when x is equal to 1, y1 through yi are IID distributed according to P1. Alright, so let me call this log likelihood ratio to be, say, z. So z, let's say zn is summation I equal to 1 to n log P1 of yi divided by P0 of yi. This is a sum of bounded random variables as we observed before. What is the expected value of Zn equal to? Of course, this has to be conditioned on let me just indicate that this is with respect to P1. One to n. Have any of you seen this particular quantity before? That's the KL divergence between P1 and P0. If you've not seen this before, it doesn't matter. It's some particular value that characterizes the closeness between the two distributions, P1 and P0. So this is nothing but n times the KL divergence between P1 and P0. So the probability of error given that the true hypothesis is equal to 1 is equal to the probability that the log likelihood ratio is less than 0 given x equal to 1, which is nothing but the probability that Zn minus the expected value of Zn is less than minus expected value of Zn given x equal to 1. I've just subtracted expected value of Zn from both sides. Right? And I know that Zn is a sum of independent bounded random variables. So this is of the form probability Zn minus expected value of Zn is less than minus delta, where delta is just expected value of Zn. So by Hoeffding's inequality, I can bound this by 2 times e to the minus delta square, which is expected value of Zn square times some universal constant divided by the sum I equal to 1 to n of the corresponding, so Zn is a sum of random variables, right? These are the bounded random variables in question. Log, or let me call them ki square right, and this is in square times the KL divergence between P1 and P0 the whole square divided by, what can I say about KI? So I know that mod log P1 of y by P0 of y, this is less than or equal to, yeah? I have some assumptions on P0 and P1, right? Right, so this is less than or equal to log 1 by P0 or log 1 by P min. Right, so this is less than or equal to n times log 1 by P min. So this is equal to 2 times e raised to minus n times the KL divergence squared divided by log 1 by P min. So as long as P0 and P1 are sufficiently spaced apart, the probability of error decays exponentially in M. Alright. And in this whole analysis, we didn't really assume anything about the distribution Py, except from the fact that the probabilities are all strictly greater than 0. That was the only assumption we required. Right? Any questions? Okay, so Hoeffding's inequality is very useful in such scenarios. Even if you don't know the actual distribution at hand, you can still derive very nice bounds on the performance of such randomized algorithms or statistical tests. I'm sorry? Correct. So this is in the denominator, it's ki square, so it should be log square 1 by p. Yeah, thanks. Okay, so if there are no other questions, then maybe let's stop here.
How do we bound k square to 1 by log 1 by p?
So I used the fact that what we had over here, for a bounded random variable, the Subgaussian norm of a bounded random variable is some universal constant times the bound. Right? That's all that I use. So of course I'm off by some universal constants, but I'm not being very careful with keeping track of those universal constants.